Report on Chang'e 5, History, Present and Future. Introduction. Chang'e 5, launched by the China National Space Administration CNSA in December 2020, represents a significant achievement in lunar exploration. This mission marked China's first lunar sample return mission and the first lunar sample return since the Soviet Union's Luna 24 in 1976. The mission's primary objective was to collect lunar samples and return them to Earth, providing invaluable insights into the Moon's geology, history, and the broader solar system. Historical context and mission objectives. Background. The Chang'e program is named after the Chinese moon goddess and has been a cornerstone of China's lunar exploration strategy, which consists of 4 stages: orbiting the moon, landing and deploying rovers, returning lunar samples, and in situ resource utilization. Chang'e 5 is part of the 3rd phase, focusing on sample return. The mission was initially slated for launch in 2017 but faced delays due to a launch vehicle failure. After the successful recovery of the Long March 5 rocket in late 2019, Chang'e 5 was launched on November 23, 2020. Objectives. The main objectives of Chang'e 5 included: 1. Collecting approximately 2 kilograms of lunar samples from the Oceanus Procellarum region, specifically from a volcanic area near Mons Rumker. 2. Conducting scientific analyses of the samples to enhance understanding of the Moon's geological evolution and its potential resources. 3. Testing new technologies for future lunar exploration missions. Mission timeline. 1. Launch, November 23, 2020, Chang'e 5 lifted off from Wenchang spacecraft launch site on Hainan Island. 2. Lunar orbit insertion, November 28, 2020, the spacecraft entered lunar orbit. 3. Landing, December 1, 2020, the lander successfully touched down on the Moon's surface. 4. Sample collection, December 3, 2020, the lander collected samples using a drill and scoop. 5. Sample transfer, December 5, 2020, the ascent vehicle docked with the orbiter to transfer the samples. 6. Return to Earth, December 16, 2020, the return capsule landed in Inner Mongolia, completing the mission. Key discoveries and scientific significance. Sample analysis. The samples collected by Chang'e 5 are approximately 2 billion years old, significantly younger than those returned by the Apollo missions, which date back between 3.1 and 4.4 billion years. This younger age allows scientists to study the Moon's geological processes during a time when multicellular life was emerging on Earth. Key findings from the sample analyses include: identification of new lunar minerals such as Chang'e Y and unique forms of titanium compounds. Evidence of volcanic activity and the presence of hydroxyl molecules suggesting possible water in the lunar soil. Insights into the Moon's thermal evolution and geological history. Filling crucial gaps in lunar chronology. These findings enable researchers to better understand the Moon's history and its relationship with Earth and other celestial bodies in the solar system. Extended mission and future plans. After completing its primary objectives, Chang'e 5 embarked on an extended mission to test technologies in the Sun-Earth Lagrange point L1. This extended phase aims to gather data for future missions and further develop China's capabilities in lunar exploration. Future missions. The Chang'e program is set to continue with ambitious plans that include: Chang'e 6, scheduled for launch in 2024. This mission aims to return samples from the far side of the Moon. International Lunar Research Station. Plans are underway to establish a collaborative lunar research station by the 2030s, allowing for sustained human presence and exploration on the Moon. China's long-term vision includes crewed lunar missions, further lunar sample returns, and the exploration of Mars and beyond. International collaboration and impact. Chang'e 5 has not only advanced China's space capabilities but has also fostered international collaboration. The CNSA has committed to sharing the lunar samples with global scientific communities, promoting research partnerships and collaborative studies. The mission has been lauded for its scientific rigor and international openness, with samples being made available to researchers in countries like the United States, Australia, and Sweden. Conclusion. The Chang'e 5 mission stands as a historic achievement in lunar exploration, showcasing China's growing capabilities in space science. The successful collection and return of lunar samples open new avenues for understanding our moon's history and its role in the solar system's evolution. As China moves forward with its lunar exploration program, the international scientific community eagerly anticipates the insights that will emerge from this collaboration, paving the way for future discoveries and advancements in space exploration. Counterintuitive information in the context of Chang'e 5. 1. Young moon samples. While one might expect that lunar samples would predominantly be ancient given the moon's long history, the Chang'e 5 mission returned samples that are approximately 2 billion years old. This is notably younger compared to the samples collected during NASA's Apollo missions, which date back between 3.1 and 4.4 billion years. The implication here is that the moon has undergone geological processes much later than previously thought, thus challenging the assumption that its surface is primarily ancient. 2. Geological activity. The expectation might be that the moon is largely geologically dead given its lack of atmosphere and water. However, the findings from Chang'e 5 suggest that significant volcanic activity occurred relatively recently in lunar history, as indicated by the young age of the collected samples from the Oceanus Procellarum region. This challenges the notion of the moon as a static body and suggests that it has a more dynamic geological history. 3. International cooperation. The Chang'e 5 mission, which is often viewed through a lens of national pride and competition, has a strong element of international collaboration. Many scientists globally, including those from the US, Australia, and the UK, are actively involved in analyzing the samples. This counters the narrative of space exploration as a solely competitive endeavor and highlights the potential for collaborative scientific advancement. For sample sharing, it is common to assume that countries would keep their lunar samples for national study and advantage. However, China has announced plans to share its lunar samples with the international scientific community, including researchers from various countries. This openness runs counter to the expectations surrounding nationalistic tendencies in space exploration and signifies a shift towards a more collaborative approach in scientific research. 5. Technological advancements. Another counterintuitive aspect is the method of the spacecraft's return to Earth. The Chang'e 5 utilized a skip re-entry technique which was not widely known outside of specialized aerospace circles. This method, which involves bouncing off the atmosphere to slow down, is complex and might be expected to be more associated with human-rated missions rather than robotic sample return missions. This highlights the advanced engineering capabilities of the Chinese space program, which may not align with the perception of newer space programs relying solely on traditional methods. 6. Environmental resilience of the flag. The Chinese flag deployed on the lunar surface was designed to withstand extreme temperature fluctuations and environmental conditions. The fact that it was made from a composite material and rigorously tested for a year contradicts the common notion that flags on the moon would quickly degrade. This demonstrates a significant level of detail and consideration in mission planning that goes beyond mere symbolic gestures. 7. Extended mission goals. After completing its primary mission, Chang'e 5 embarked on an extended mission to explore the L1 Lagrange point. This decision might seem surprising, as many might assume that a mission would conclude once its primary objectives were met. However, this reflects an understanding of the broader utility of spacecraft, allowing for additional scientific exploration and technology testing beyond the immediate goals of lunar sample return. 8. Focus on resource utilization. The long-term plans of the Chinese lunar exploration program include in situ resource utilization and constructing an international lunar research station, which may counter the idea that lunar exploration is primarily about scientific discovery. Instead, it indicates a strategic outlook towards sustainable lunar presence and resource use aligning with future ambitions for human exploration and potential colonization. 9. Technological parallels with Apollo. While the Chang'e 5 mission is often seen as a contemporary achievement, it utilized a spacecraft architecture that draws parallels to NASA's Apollo missions, which is unexpected given the technological advancements in the decades since Apollo. This reliance on older but proven technologies signals a pragmatic approach to mission design that prioritizes reliability over untested innovations. 10. Public perception of space exploration. Lastly, the public perception of space exploration tends to focus on grand missions and the race for the moon. However, the Chang'e 5 mission emphasizes the importance of incremental advancements in space technology and scientific understanding rather than a singular race. This nuanced view challenges the oversimplified narrative of space exploration as a contest between nations, showcasing it instead as a complex tapestry of research, technology development, and global collaboration. In summary, the Chang'e 5 mission provides a wealth of counterintuitive insights that challenge common assumptions about lunar exploration, international cooperation, and the nature of scientific inquiry in the context of space programs. The Chang'e 5 mission, launched by the China National Space Administration (CNSA) in 2020, represents a pivotal moment in space exploration, particularly regarding lunar studies. While many aspects of this mission have been covered in reports, several important elements are often overlooked by the general public and even by experts in the field. Below, I will highlight these overlooked details and explain their significance. 1. Geological implications of sample age. One of the most frequently discussed aspects of Chang'e 5 is the age of the lunar samples, approximately 2 billion years, which is significantly younger than those returned by the Apollo missions. However, what is often glossed over is the geological implications of this age. The younger samples allow scientists to bridge a 2 billion year gap in lunar geological history, which is crucial for understanding the moon's volcanic activity and the thermal evolution of the moon itself. Significance: the ability to analyze these younger samples helps to refine models of lunar development and can offer insights into the conditions present on the moon when multicellular life was emerging on Earth. This connection between lunar and terrestrial geological processes enriches our understanding of planetary evolution across the solar system. 2. New mineral discoveries. Chang'e 5 returns samples containing new minerals, specifically Chang'e Y, and 2 distinct structures of titanium dioxide. The identification of these minerals is not just an academic exercise, it opens new avenues for understanding the moon's geological diversity and the processes that formed these materials. Significance: discovering new minerals can have profound implications for lunar resource utilization, particularly in the context of future lunar bases or mining operations. Understanding the mineral composition can lead to better resource management strategies for in situ resource utilization, ISRU, critical for sustaining long-term human presence on the moon. 3. Extended mission and technological testing. After completing its primary mission, Chang'e 5 undertook an extended mission to the Sun-Earth L1 Lagrange point and later tested technologies in a distant retrograde orbit around the Moon. While the primary mission garners the most attention, the significance of these extended operations is often undervalued. Significance: the extended mission serves as a testbed for technologies that will be critical for future missions, including those aiming to establish a permanent lunar presence or conduct more complex explorations. By successfully navigating and conducting operations in these orbits, CNSA is laying the groundwork for subsequent missions, including potential crewed missions to the Moon. 4. International collaboration and sample sharing. The Chang'e 5 mission also marked a significant step in international collaboration in space research. CNSA has indicated its willingness to share lunar samples with international partners, which is a relatively new approach for China in the context of its space program. Significance: this openness can foster international cooperation in space science, promoting a more collaborative atmosphere in a field that has historically been competitive. Sharing samples and data can lead to a more comprehensive understanding of lunar geology and may influence global policies regarding space exploration and resource management. 5. Cultural significance and national pride. Beyond the scientific achievements, the deployment of the first Chinese flag on the Moon during the Chang'e 5 mission represents a cultural and national milestone. The flag's design, made from materials capable of withstanding harsh lunar conditions, embodies a blend of scientific achievement and national pride. Significance: this act is symbolic of China's aspirations in space exploration, representing a significant achievement for the country and its space ambitions. It consolidates China's position as a major player in global space exploration, inspiring a sense of unity and pride among its citizens. The cultural implications of such missions can influence public interest and investment in science and technology sectors. 6. Implications for future lunar bases. The Chang'e 5 mission's findings regarding lunar soil and potential water content are often noted, but the broader implications for establishing lunar bases are sometimes overlooked. The discovery of hydroxyl in the samples indicates that the Moon may have water molecules embedded in the soil, which is essential for future human missions. Significance: understanding the distribution and availability of water resources on the Moon is critical for sustaining human life and conducting long-term missions. Water can be used for drinking, growing food, and as a resource for producing fuel. Thus, the implications of these findings extend beyond scientific inquiry to practical applications for future lunar colonization. 7. The role of technology in mission success. The technological advancements that enabled Chang'e 5 to succeed, like the skip re-entry technique, are often overshadowed by the mission's scientific results. This method of re-entry allowed for a safer return of lunar samples by reducing the stress on the spacecraft during atmospheric re-entry. Significance: these technological innovations are not just relevant to the Chang'e 5 mission but serve as valuable lessons for future missions. The successful application of such techniques can enhance the safety and efficiency of interplanetary missions, influencing spacecraft design for future explorations of Mars and beyond. 8. Environmental considerations for future missions. As space exploration increases, the environmental impact of these missions is becoming a growing concern. Chang'e 5's operational protocols and the decision to crash the Ascender module into the Moon to avoid space debris highlight an awareness of these issues. Significance: the approach taken by CNSA could set a precedent for responsible space exploration practices, emphasizing the importance of minimizing space debris. This proactive stance may influence future international regulations and guidelines on space missions, contributing to long-term sustainability in outer space. Conclusion: the Chang'e 5 mission is a landmark achievement in lunar exploration with implications that extend well beyond the immediate scientific findings. By recognizing and emphasizing these often overlooked aspects, such as geological implications, mineral discoveries, international collaboration, and responsible exploration practices, we can gain a more comprehensive understanding of the mission's significance. As we look to the future, the lessons learned from Chang'e 5 will undoubtedly shape the trajectory of lunar exploration and the broader quest for knowledge in our solar system. 1. Historical significance and technological achievement. Chang'e 5 represents a pivotal moment in lunar exploration history, marking China's third successful lunar sample return mission and the first since the Soviet Union's Luna 24 in 1976. This mission not only demonstrates China's advancing capabilities in space technology but also signifies a resurgence in global lunar exploration. The mission's architecture, inspired by NASA's Apollo program, involved a complex sequence of operations that included landing, sampling, ascent, and return, showcasing China's technological prowess and ambition in space exploration. 2. Scientific contributions and discoveries. The samples collected by Chang'e 5, which are approximately 2 billion years old, provide crucial insights into the Moon's geological history and evolution, particularly during a period when multicellular life was emerging on Earth. The identification of new lunar minerals such as Chang'e Site Y and unique titanium compounds enriches the scientific understanding of lunar geology. These findings are important for calibrating lunar and planetary chronological tools and understanding the processes that shape not only the Moon but also terrestrial planets in the solar system. 3. International collaboration in future missions. The Chang'e 5 mission has fostered international collaboration in lunar research, with China open to sharing its samples with global scientific communities. This approach aligns with the trend of collaborative space exploration, emphasizing that scientific inquiry transcends national boundaries. Furthermore, the mission sets the stage for future projects including Chang'e 6, which aims to return samples from the Moon's far side, and long-term plans for an international lunar research station, indicating China's commitment to becoming a leader in lunar exploration. For extended mission and future prospects, after completing its primary objectives, Chang'e 5 embarked on an extended mission to explore the Sun-Earth Lagrange point L1, conducting tests for future lunar missions. This phase not only serves to enhance China's operational capabilities in deep space but also lays the groundwork for future exploration initiatives, including crewed lunar missions planned for the 2030s. The strategic exploration of L1 and the Moon's distant retrograde orbit reflects China's long-term vision for sustainable lunar exploration and resource utilization, positioning the country as a major player in the next era of space exploration. 1. Apollo 11 mission 1969. The Apollo 11 mission conducted by NASA was the first manned mission to land on the Moon. Astronauts Neil Armstrong and Buzz Aldrin landed on July 20, 1969, while Michael Collins remained in lunar orbit. Armstrong's iconic words, "That's one small step for a man, one giant leap for mankind," marked a historic moment in space exploration. The mission not only accomplished the goal of landing on the Moon but also returned 47.5 pounds (21.5 kilograms) of lunar samples to Earth, significantly contributing to scientific understanding of the Moon's geology and the history of the solar system. 2. Luna 24 1976. Luna 24 was a Soviet lunar mission that successfully returned the last samples of lunar soil to Earth before the Chang'e 5 mission. Launched on August 9, 1976, it landed on the Moon on August 18, 1976 in the Mare Crisium region and collected about 170 grams of lunar soil. This mission was notable for its highly automated operations, which were designed to minimize human intervention. Luna 24 provided critical insights into the Moon's composition and geology, and its samples helped refine the timeline of lunar volcanic activity. 3. Hayabusa 2 mission 2014-2020. The Hayabusa 2 mission, conducted by the Japan Aerospace Exploration Agency JAXA, aimed to collect samples from the asteroid Ryugu and return them to Earth. Launched in December 2014, it arrived at Ryugu in June 2018, where it conducted observations and collected samples using a sophisticated sampling mechanism. The spacecraft successfully returned to Earth on December 6, 2020, delivering around 5.4 grams of asteroid material. This mission has provided valuable data on the origins of the solar system and the building blocks of life, paralleling the significance of lunar sample return missions like Chang'e 5 and enhancing our understanding of celestial bodies. Future outlook, predictions for China's Chang'e program and lunar exploration. The Chang'e 5 mission, which successfully returned lunar samples to Earth in December 2020, has set the stage for an ambitious future in lunar exploration. As we look ahead, several key predictions can be made regarding the trajectory of China's lunar program and its implications for global space exploration. 1. Continued lunar exploration and sample return missions. Following the success of Chang'e 5, China is poised to launch subsequent missions, notably Chang'e 6, which aims to return samples from the Moon's far side in 2024. This mission is expected to enhance our understanding of the Moon's geological diversity and history. Future missions including Chang'e 7 and Chang'e 8 are planned for the late 2020s, focusing on exploring the lunar South Pole and investigating potential resources such as water ice. These missions will likely utilize advanced technologies including robotics and autonomous systems to enhance their efficiency and success rates. 2. International collaboration in lunar research. China's willingness to share Chang'e 5 samples with international scientists signals a shift towards more collaborative global efforts in space research. Future lunar missions may involve partnerships with other space agencies including NASA, ESA, and Roscosmos, fostering a cooperative approach to lunar exploration. This collaboration could extend to establishing joint research facilities on the Moon, enabling comprehensive studies of lunar geology and potential resource utilization. 3. In situ resource utilization (ISRU). As lunar missions advance, there will be a significant focus on ISRU technologies, particularly for sustaining long-term human presence on the Moon. The Chang'e program aims to advance technologies that can utilize lunar resources such as extracting water and producing oxygen and fuel from regolith. These developments are crucial for future crewed missions, enabling astronauts to live and work on the Moon for extended periods, potentially as early as the 2030s. 4. Establishment of an International Lunar Research Station (ILRS). China has plans to establish an International Lunar Research Station by the late 2020s or early 2030s, particularly near the lunar South Pole. This facility will serve as a hub for scientific research and exploration, supporting various scientific disciplines including astrobiology, geology, and physics. The station could also facilitate missions from multiple countries, making it a cornerstone for international lunar cooperation. 5. Crewed lunar missions and the 2030s vision. China has expressed intentions to land astronauts on the Moon by the early 2030s, marking its entry into the realm of crewed lunar exploration. The Chang'e program's achievements in robotic missions will lay the groundwork for these ambitious human endeavors. The experience gained from the Chang'e missions will inform the design and execution of crewed landings, which will focus on scientific research, habitat construction, and potential resource extraction. 6. Technological innovations in spacecraft design and operations. The success of Chang'e 5 demonstrated China's capabilities in spacecraft design and operations. Future missions will likely incorporate cutting-edge technologies including advanced propulsion systems, autonomous navigation, and improved life support systems. These innovations will not only enhance mission safety and efficiency but also reduce costs, making lunar exploration more sustainable. 7. Broader implications for space exploration. China's advancements in lunar exploration will have far-reaching implications for the global space landscape. As China continues to enhance its lunar capabilities, it will challenge existing space powers like the United States and Russia, potentially reshaping international space policies and collaboration frameworks. The growing competition may spur advancements in technology and exploration strategies benefiting the entire scientific community. 8. Increased focus on planetary defense and deep space exploration. With the experience gained from lunar missions, China may extend its focus to broader planetary defense initiatives and deep space exploration. The knowledge and technologies developed through the Chang'e program could be instrumental in identifying and mitigating threats from near-Earth objects (NEOs) and planning future missions to Mars and beyond. Conclusion. The future of China's Chang'e program and lunar exploration is characterized by ambitious plans for continued exploration, international collaboration, and technological innovation. As the program evolves, it will not only enhance our understanding of the Moon but also play a pivotal role in shaping the future of human space exploration. The next decade will be critical as China positions itself as a leader in space exploration, setting the stage for a new era of scientific discovery and international cooperation in the cosmos.